Just that on the bottom. Yeah.
All right, please take a seat. Please take your laptop. Welcome everyone to this discussion session, which will be about galactic analogs of FRBs. Both myself and Myles will be coordinating this, and hopefully you will be doing most of the talking. So I'm Jason Hessels at McGill University, also affiliated with the University of Amsterdam and ASTRON.
And I'm Myles Sherman. I'm a grad student at Caltech, mainly working with the DSA 110.
You can barely hear us.
That's my fault. Yeah, I'm Myles Sherman. I'm at Caltech. I'm a grad student, mainly working on the DSA 110. Forgot it doesn't.
No worries. Okay. So what Myles and I have done is we've come up with 4 themes. The first theme is about pulsars and compact objects in the Milky Way. The second is about magnetars. Surprise, surprise. The third is about pulsar wind nebulae, supernova remnants, and their potential relation to PRSs. And then the fourth is about the LPTs. And these are topics that we've been hearing about all day. So what we would like to do is maybe spend 10 or 15 minutes on each of these topics. And what we are going to do for each of them is we're just going to spend 2 minutes motivating the topic a little bit. And then we want you guys then to raise points. And hopefully someone will raise 1 point. And then we will take some reactions to that point before we move on to another topic, so that we don't just bounce around between random remarks, that we try and steer the conversation a little bit. So the first question that we have out of the 4 is to what degree can pulsars and compact objects in our own Milky Way, how far can we stretch this analogy towards FRBs? So we know that galactic neutron stars have actually different types of radio pulses they make. The pulsars that were discovered already back in the 1960s have this kind of canonical polar cap radio emission, and as the star rotates, we see these pulsations. But we know of giant pulses as well, and there's reason to believe that that comes from somewhere different in the magnetosphere or further out. We have magnetar radio pulses as well, and magnetar bursts, as we've seen. So are these, can we just ramp up the luminosity and we get FRBs? This is a question. And to remind you, we've seen some versions of this parameter space many times throughout the conference. A lot of the morphology that we see between pulsars, magnetars, and FRBs is similar, but don't forget that the luminosities are off by a factor of a trillion. So is that a problem or not? Might be. Next point is some galactic neutron stars are in interacting binary systems. So when we talk about dispersion measure variations and rotation measure variations, we need to remember this, right? So we have neutron stars that experience Roche lobe overflow, accretion through Roche lobe overflow. We have wind accretion in more massive systems. We also have neutron stars that have very low or high mass binary companions. We'll come to supernova remnants and all of that stuff later. But in terms of interpreting DM and RM variations, we should keep this in mind. And lastly, yeah, like I was saying, does similarity in phenomenology necessarily mean that the source type is similar? So we'd like to open up the floor to some points and reactions to this. Again, under the topic of how far can we push this analogy of pulsars and compact objects as we know them in the Milky Way for understanding FRBs. So who would like to open the floor? Yeah.
Hey, this is Pawan from Sunburn University. Yeah, so just to open up the conversation, I think the first thing in terms of galactic analogs, the first source that comes to my mind is 1259 - 63, which can explain the...
Yeah, do you want to explain what that source is for people in the audience who might not know?
It's a pulsar B star system, and every time it goes past B star, a decretion disk, you would see that there is a flip in RM sign, which is kind of used as an analogy for 190520B flip in the sign of RM. And we have been seeing more increasing sources of FRB's repeaters, especially, which have been showing this flip in sign of RM and finding galactic analogs. I just want to know what others would think in terms of finding such really weird sources in our own galaxy, and then try to see if, at least canonically, some of their properties match with what we see with repeating FRB sources, which is fairly straightforward compared to non-repeaters. Absolutely. So yeah.
Yeah, so there are a number of young pulsars in the galaxy that have a massive stellar companion, and they have large variations in DM and RM. That's a great source. I think it disappears when it gets close to periastron, right? Yeah. And importantly, most massive stars form in binary systems as well. So as long as they're not disrupted, it shouldn't be a surprise that you have a binary companion. Would anyone like to react to that point? Is this a plausible model for some of the FRBs? And think of, like, for instance, the third repeater in its 16-day periodicity. Yeah, Vicky?
Well, so 1259 minus 63 is an interesting case because it's a several-year orbit and, way wider. The eccentricity is, I think, 0.86. So the periastron distance, it's we could work that out. But in a 16-day orbit, that's probably a much smaller orbit. And so, but in 1259 minus 63, the phenomenology is you have, first of all, huge scattering variations, huge RM changes, huge DM changes as a function of orbital phase, particularly near periastron. And if you look at a recent paper by Ketan Sand et al. From CHIME data at the 16-day repeater, you don't see any variation of scattering and DM with phase. Now, I know there are models that could, in principle, avoid that, but I just feel like, at least naturally, you might expect some sort of hint. So perhaps it's not a showstopper, but I think that's a relevant clue.
Oh, maybe we'll go to, sorry, this is just closer, and then we'll come to you. Yeah, first go for Rob. Yeah.
Great. Yeah, I was just gonna say, I know 1259 minus 63 often gets talked about. A lot of Black Widow and Redback pulsars show very similar things. It takes very little plasma to cause what we perceive as crazy RMs. If you have a companion, it's going to have a much larger magnetic field than you see in the ISM. So I'm not suggesting that FRBs have to be in spider systems, but for instance, in Terzan 5A, it's less than 1 DM unit change across the orbit. Most of the orbit is nice and quiescent, and then less than 1 DM unit, no change in scattering, basically no change in DM. And you get absolutely wild changes of first hundreds of RM units, and then enough that you get parity conversion. So just the point, the lack of DM variation does not mean that there's not plasma that can cause, for instance, the RM variations at the order that we see.
For sure. And as Myles ferries it up there, I'll just mention that, like, those spider systems have mini eclipses that are sporadic and which kind of indicate that the plasma is magnetically threaded as well, right? Yeah.
So I think there are some things that we can learn about potentially non-repeaters by studying these galactic neutron stars. When we think of magnetars, we automatically associate them with neutron stars with 10 to the 15 Gauss magnetic fields, but that need not be the case.
Oh, sorry, could you please introduce yourself as well?
Naveen Sridhar from Stanford. Yeah, so when we talk about magnetars, we automatically associate them with 10 to the 15 Gauss neutron stars, but that need not always be the case. There are some neutron stars, particularly PSR 1846 minus something in the supernova remnant KES 75, which was long thought to be a typical rotation-powered pulsar, but then it showed magnetar-like bursts only for a very short period of time. That is, the outburst required more energy than the rotation power. So it's possible that seemingly normal neutron stars could occasionally become magnetars and then become regular neutron stars or just show magnetar-like behavior. So this could be something that's perhaps happening in many apparent non-repeaters, something that we can learn from. So just throwing out there, that's it.
Okay, thanks. And thanks, Naveen. And I think Barack had a comment. You can just risk it. Oh.
Hey, Barak Zakai.
Can you project a bit?
Yes.
Yeah.
So to me, the biggest question. What? I'm Barak Zakai. To me, the biggest question in saying, oh, an FRB is my galactic friend X, is that if I have 100 examples of galactic friend X, why are they not FRBs? And I think that this is an important clue in the discussion. Why don't we have like many of them in the galaxy? There's something that needs to be very rare, and we are not putting the emphasis on
So
it.
on that topic, does someone know off the top of their head? Imagine most FRBs are in spiral galaxies, which is, we know is not completely true, but imagine most of them are. So how many galaxies do you need to have on average before you find one that has an FRB in it? What's the number?
Per galaxy per century?
And who are you?
Daniele Micheli from Marseille, France. I think papers in the literature reported 2 per galaxy per century, something like that.
Seems high. Okay, Mawson?
Well, depends on the luminosity, of course.
Yeah. Oh.
Yeah, I'm Molson Simons from here at McGill. I think I track with Daniele's point in that, like, if the all-sky rate for like above like 180 to 39 bursts, I think in the Chime first catalog was like 500 per sky per day. If you're sensitive out to like a redshift of 0.5 to bursts like that, that's a lot of galaxies and not a lot of FRBs. And so like, I don't know the fact that we haven't found any in the galaxy is necessarily like, I don't know if we need to explain that tension.
Can we go to Adam?
And actually, before we go to Adam, I just wanted to mention on that, there's also seems to be a, dependence on the type of galaxy. Of course, like there have been these long, very long observations of nearby galaxies as well that haven't really detected anything. The Northern Cross, survey was just one that we heard about, as well as some from like the DSN telescope, where you're looking at regions that should have a lot of FRBs and maybe don't.
Hi, this is Adam Dong from NRAO. I agree with Barak in that like they should be really rare, and I think one thing is that there's these hyperactive repeaters, and with for example a rat, you'll find a rotating radio transient, you'll find a period, like you get 3 pulses and you get a period out, right? But with these hyperactive repeaters, we just saw 11,000 bursts, and they said they may have a period, right? Like it really doesn't seem like anything in pulsar land except for the SGR 1935 bursts that aren't coming on phase, right? So that's just my comment.
Okay, thanks. Is there a final comment on this before we move to the next topic? Please introduce yourself.
I'm Dotan from Weitzman. I think in the same sense of something that should be typical or maybe so typical and low energy that we don't see it in FRBs, but extremely rare in the galaxy. Do we know to characterize like how the rate of bursts gets when you go to very low and to barely detection, and how does those galactic analogues, really the tail of the highest energies, highest energy bursts that they can emit, like.
Yeah, so there are some galactic pulsars that the energy distribution starts to flatten as you go to the brightest pulses. So you could say, oh, maybe it extends really far out. Some of the hyperactive sources that FAST has looked at, they're claiming to see a turnover in the energy distribution, but they see like a characteristic lowest energy already, so that it wouldn't extrapolate all the way down to pulsars. Yeah, it's a really important point. I think the answer is that is a point of study still. Figure that out. Yeah. Okay, then thanks for your comments, and we will move to the next topic, which will be led by Myles.
We'll switch. All right. Yeah, so this is kind of following on, you know, the things we've been discussing with pulsars as we've sort of naturally started moving towards magnetars. So I'll just kind of motivate that a little more. So again, there's roughly 30 magnetars, depending on how you count, in the galaxy. A small subset of these are radio emitters. Most of them are, you know, emitting in X-rays, hard X-rays, and then shorter X-rays for their outbursts. And as you can see from this plot that we've seen a couple of times in the luminosity versus pulse width, they you know, magnetars kind of generally cluster around, you know, around 1 Jansky kiloparsec squared. But then you have SGR 1935 that kind of spans the gap between magnetars and FRBs. And it's curious why we don't detect a lot more in that range. If the magnetar FRB model, you know, has any weight, then it might suggest there's multiple formation channels for FRBs, like there might be for magnetars. And there are a number of magnetospheric models that are associated with magnetars, as you heard about earlier in the week. So some of the questions, of course, are surrounding, you know, the main link that we have, of course, is SGR 1935. We saw this earlier during a talk. And a couple of the questions that we were thinking about are, you know, in general, how likely or universal is the FRB magnetar model? Is it something that applies in all cases or only to like the hyperactive repeaters? Is there some distinction that we should make or somewhere that we can draw the line? How robust is our identification and understanding of magnetars? I mean, we only have 30 of them. So is that, you know, what are observational biases there? Are we only detecting certain types of magnetars? And what is our distinction between pulsars and magnetars? As was just mentioned, you know, pulsars can enter these magnetar-like phases as well. How do we interpret the luminosity difference that I just showed between magnetars and FRBs? And how do we search for high energy counterparts, you know, since most magnetars are emitting in high energies? And then finally, how can we unify, you know, the earlier evidence of magnetar or early time evidence of magnetars, so like millisecond magnetars, with the later stages of magnetars that we observe these periodic emission from? That was kind of touched on in one of the later talks, that it's very, you know, difficult to get a scenario where you can have a millisecond magnetar, say, in FRB, or be responsible for FRBs. So how do we start to unify like millisecond magnetars with the later time scale magnetars? Yeah, any thoughts on any of these? Right here. Sorry. And please introduce yourself.
Hey, this is Pavan again from Swinburne. So I just wanted to probably kick off by alluding to the fact that there is still a lot of observational bias when we try to look at magnetars, because in terms of catching a burst, which is FRB-like, all-sky monitor kind of a thing, which always stares at those magnetars as something essential in order to sort of bridge that gap. And I think smaller dishes, some work by Hyperflash, which if you have smaller dishes, then picking a magnetar and then making sure that we accumulate enough observing time in order to see if there is any sudden burst, that is probably the way to go in terms of like bridging that gap. Just this is purely from observational perspective, but of course there might be different thoughts on that.
Yeah, it's a great point. And somebody had recently messaged us in the Slack channel that, you know, it's really important to get time on radio quiet magnetars as well, in order to to get time on radio quiet magnetars. We're definitely biased towards the more radio loud ones where we see an outburst and, you know, we'll detect that and start to follow it up with X-rays. But what about the ones that we're not always getting a huge outburst from, or do they have, you know, lower luminosity emission?
Hi, it's Molson Simons again. And so I guess like just seeing the statement before about there being kind of only 30-ish magnetars in the galaxy, I guess like we then have to reconcile with the idea that we're never going to have enough time to like probe into the part of the energy distribution that would emit FRBs at a substantial rate, in that if we're only seeing FRBs at, you know, so many hundreds per sky per day over this number of galaxies that we really probe out to, that trials factor from the number of galaxies you get is like adding to your exposure in a way where the same amount of time then divided up amongst like 30 magnetars in the galaxy is going to be so long that like you'll never probe that like regime statistically. And so I guess we need a different way to think about whether or not these magnetars could be generating those high energy pulses on a longer timescale.
Yeah, that's a great point as well. And it might come down to, you know, boosting our population, or whether that's boosting our galactic population, but boosting nearby nearby observations in nearby galaxies. That is, anybody have a follow-up on that?
Andrea Possenti from INAF. I just got anticipated by what said. No. It's reinforcing what I was about to say about the fact that indeed, if you look at the phenomenology of the single pulses in the radio magnetars, it's really striking the similarity with the very vast phenomenology of the repeaters, especially. And but there is this big issue of counting how many of them, which might be related to the different level of intensity of the emission. There might be a gradual distribution, or maybe not so gradual, between those which doesn't emit almost anything in terms of radio magnetar, and those which emit like radio magnetars when there are the X-ray outbursts, and those which are maybe in specific stage of magnetar life that every now and then emit very strong bursts and can be seen very far away.
Yeah, and I think you know, characterizing that distribution has been tricky also with our classification of magnetars, like, and how we actually distinguish between magnetars versus pulsars versus, like, you know, an X-ray transient that is unidentified. Like, how do we fill in the distribution when it's not always clear what falls into what category? Does that make sense? Oh. Yeah,
Casey Law from Caltech. Yeah, this moving down the luminosity distribution point is really good, I think. And there is one other way to work around it, which is that, of course, all the radio emission is beamed. So if we can provide different perspectives on a source, then you would actually have independent samples of the beamed emission, right? So like, I think effectively what you want to do is like some sort of radio calorimetry of a source, right? Identify a source and then figure out how you would bound the radio energy output. But I don't know how that works, because you'd have to see it from different perspectives or have something else see it from different perspectives and then measure the energy output that way. But that would be a way to get down in the luminosity distribution, right? Yeah.
Yeah, so good.
Just one point related to this. If you go back to the previous graph, I'm not sure if everyone completely appreciates this, but, you know, Chime and Stare saw this very bright burst from SGR 1935 that was maybe like 30 times less luminous than, you know, your typical extragalactic FRB. FAST saw some radio pulses at the period of the magnetar that are kind of around where the red dots are for rats. But Vesterbork also saw two bursts that are kind of in between the two. And that one single source emitted radio bursts over a factor of 100 million in luminosity. So, you know, you could imagine maybe that means that neutron stars can emit over trillions of factors in luminosity. Yeah.
I think Yuri and then.
Thank you. So if you want to play around with this, then I say download FRB Poppy. You can build your own FRB population. You can put in the luminosity distribution, and you can see that you can connect it to the magnetar density that we have. So I think it's doable.
A couple comments. One is, well, I think the difference in luminosity of the bright FRB or the bright FRB-like event from 1935 is, I mean, I thought I heard factor of 30, but I think it's more like a factor of 10 to the 6 to 10 to the 9.
Factor of 30 to like the weakest extragalactic.
Oh, to the weakest. Okay, yeah. Yeah. Then on your next slide, you're asking, is there biases in the galactic magnetar population? And most of them were found by bright X-ray bursts. So and those identifications are really unbiased because they're found by gamma ray burst monitors that were designed to see everywhere, and they always tend to find them right in the SGR or magnetar types right in the plane. But they're biased against those that produce X-ray bursts. That was one point. And then I had a question for the, I think, was it Marcus, who presented on 1E 1547? Yeah. Oh, you're right. Isn't that funny? So my question was, you said, oh, it shows all this phenomenology, everything, and you said drifting, and you said it very quickly, but does it actually show the sad trombone kind of stuff that we see from repeaters? Because you didn't show an example of that.
Okay, this is Marcus from Swinburne. So the drifting that I think I mentioned was more due to subpulse drifting from one rotation to the next. And then the one plot I had, which had what might look like some sort of sad trombone effect, we can't tell if those individual components are from one rotation or several rotations averaged together because it was fold mode data.
The answer is no.
No.
Okay, you have a million bursts from it, and you've never seen downward drifting sad trombone things, right? Just
Yes.
right, I understand.
Yeah.
But nobody's seen that from a magnetar, is all I'm saying.
Yeah, no, that is a really interesting point because, I mean, what distinguishes the phenomenology, the phenomenology that we see in radio magnetars versus FRBs? I mean, right off the bat, like radio magnetars are periodic, so like that's already one thing that we can, in general, are periodic. So like, what else, distinguishes them? We have one here we can maybe pass. So we'll take.
I'm going to do it to Brian.
We'll do maybe 2 more comments and then move on to the next topic.
Brian Gainsler, University of California, Santa Cruz. So we've had 3 magnetar giant flares since 1979, one in 79, one in the 90s, and one in 2004 that were all much, much brighter in energies than 1935. Is it right that we really don't know what those were doing in the radio at those times? And that, could there have been even a burst storm lasting, a week and we wouldn't have known?
Yeah, so
do you want to respond to that, Vicky?
We'll do this last response. And
yeah, at the time of the 1806 -20 giant flare, the Parkes telescope was observing, not pointed at it, but the source was in the side lobe. And there's a paper, Tendulkar et al., Sriharsh led it with Chitrang and myself, and got those data. And if there had been an FRB type event, depending on exactly what you know about the side lobes of Parkes, but he did some really great calculations, you would have seen it.
So we're going to go ahead and, for sake of time, move on to the next topic. But yeah, thank you. This is some great discussion.
Great. Okay, so our next topic was supernova remnants, pulsar wind nebulae, and persistent radio sources in the case of FRBs. So I guess maybe one of the first things to say, maybe I'll even jump to the second point first. I mean, it would not be very fun being a radio astronomer if you were in a galaxy with a PRS, because these are many, many orders of magnitude brighter than the crab. And, if you work with a telescope like LOFAR, for instance, like you see the crab in the side lobes of the antennas. So imagine having something that's 100,000 times brighter than the crab. It gets pretty spicy. It'd be like trying to be an optical astronomer observing during the day. It wouldn't not be very, very, very rewarding. Sorry? And it's variable as well. Yeah. Well, I'm talking about the persistent radio source. Well, there's due to refraction. Yeah. Not on like super short time scales, but yeah. So so these are pretty spectacular things. And I think that's probably an argument that, well, we certainly don't have a PRS FRB in the Milky Way. I think we would definitely know that if there was something of that luminosity in our, regardless of beaming, right? We would just know that there was something like this in the Milky Way. So we have lots of galactic supernovae and pulsar wind nebulae. Hopefully Brian will chime in at some point. These are different things, but they're related things. One is created by the pulsar wind, the other is from the initial explosion. It seems like magnetars are less associated with nebulae and yeah, well, at least with nebulae, perhaps not with supernova remnants. Sorry? One X-ray nebula was the comment. Yeah. Okay, and we'll come to you in a second, Shami. So we don't have particularly extreme pulsar wind nebulae in our own galaxy. Like, the Crab is kind of the most extreme example, I think, and there are a few others that are kind of comparable. But there has been some very interesting work done recently, for instance, by Dylan Dong and Greg Hallinan, starting to find what look like plausible extragalactic pulsar wind nebula candidates. So that might be, at least the nearby universe, if we move a little bit beyond galactic analogues to just, tens of megaparsecs or so, there's maybe something to be learned there. So to start this discussion, I guess, Shami, if you have your hand up, do you want to go first?
Yeah, sure. Can you guys hear me okay?
We can hear you great.
So I was beginning to wonder, have we gone long enough that we should be able to see time evolution in the examples of the PRSs we have, and not seeing them fade, or what limits we have on them fading, and what that's starting to say about what the sources can be?
Yeah, well, Gavia, would you like to comment on that?
Hi, this is Kavya Shaji from University of Sydney. So yeah, the long-term data we have on a PRS is of R1. So we have now it's been nearly 10 years of observation data we have on PRS flex density. But we can see a flex density variation in short time scales. But in long terms, we are not seeing any evidence of long-term variation in the flux density. So yeah, it's kind of stable, and the short-term variation we are seeing is consistent with predictions from refractive scintillation. So yeah, the flux density is stable for PRS of R1.
Okay. Other comments? Yeah, Matthias.
Hi, this is Matthias from University of Toronto. I guess one interesting aspect is that we're still at the era of the Crab you use as an example is kind of our staple example of bright PRS in our own galaxy, except that there's this lack of very young pulsar winds and you mentioned Dylan Dong's paper as a candidate that's probably a couple decades. But we're reaching a point now that we've had kind of these all-sky optical surveys that have been looking at least have been establishing a sample of core-collapse supernovae in the local universe that are now exhibiting kind of this radio rebrightening at late times, like 5 to 10 years post-explosion, which is kind of in line with the timescales that you'd expect your ejecta to become optically thin and you get a pulsar wind that is emerging. So I think that we're early on the researches, especially towards the superluminous supernovae, but I think a promising avenue could be going towards these, doing targeted searches at these late time radio rebrightenings, because at this point, if they're optically thin, then you can kind of test this young pulsar or young magnetar model more.
Yeah. Great, thanks, Matthias. Any reactions to that or other directions? Yeah, Lauren, please. Yeah.
Yeah, I want to second what Matthias says. Oh, I'm Lauren. Yeah. I never have to introduce myself when I hold this. Yeah, I'm Lauren Rhodes. I'm at McGill. Yeah, I just want to second what Matthias says, but also that unfortunately we won't be able to use this surveys like the VLA Sky survey to do these sorts of tests because these things are just too faint. Like if you look at the PRS associated with R1, Alex's new one as well, they do really need their own dedicated campaigns. So please write to your lovely tax and ask for time.
I would imagine that maybe DSA 2000, well, DSA 2000 will get deep enough to pick this out, right?
But if we want to monitor these things or find them in the first place, maybe we need to look a little sooner. But yeah, like the current surveys won't be able to find them, I think, in most cases. Yeah.
Okay. Yeah, watch your language. Okay, we'll go to Naveen first. Actually, I'm interested also to know, Naveen, if you think that the stability of the PRS is difficult in terms of your model of a hyper-Eddington accreting source.
It's not really. The prediction from 4 or 5 years ago was that the luminosity would barely increase, an extremely small increase over the next few years, and that's very much dependent on the choice of parameters.
It depends on kind of the evolution timescale of the binary, right? Because it's dependent on the mass transfer.
Exactly. So you cannot predict what it's going to be like 10 years from now, assuming an initial state which is going to change every year. So it has to be iteratively done. So it's a small change in the parameters could easily satisfy the observations.
Are you frustrated that I only put up a picture of a pulsar wind nebulae? Should I have put up a picture of SS433 as well? Or?
I would love to see an SS433 because we have seen many such persistent radio sources surrounding accreting engines. So there's something that we could learn about PRS from accreting engines, hyper-Eddington accreting engines. Many extragalactic ULXs, for example, that beautifully show these PRSs around them.
Yeah, an FRB from a ULX would be that would be a smoking gun, I guess.
Yeah.
Okay, then we'll go to Matthias, and then we'll go to Zorwar.
This is Matthias, sorry. This is just kind of going back to what Lauren was saying before. While I do agree that there's a lot of these events and not necessarily, you would have to do dedicated follow-up. You can kind of be strategic in terms of what targets you want to go after. Like you wouldn't necessarily go after a type 2 core collapse that's happened in the last 10 years because you would expect the ejecta to still be relatively optically thick. But you would then maybe say, I'm going to go for type 1Bs or type 1Cs or the broadline events that are going to be more rapidly expanding, and that sample is significantly smaller. It's still a substantial amount, and the VLAS, the rebrightening that you would expect also does hit can hit above multiple millijanskys, which is detectable in VLAS. And there's, I think, a paper from 2021, Stro, I can't remember the first name, but they detected late time using VLAS and kind of argued in favor of various models. Yeah.
Thanks.
Yeah, this is Arwadi Singh, University of Maryland, NASA Goddard. I was just going to say, I don't know if the ULX would be a smoking gun, right? Because there's pulsating ULXs and they're most likely magnetars in a ULX. Pulsating ULXs, yeah. Yeah, but they could have a burst, right? A magnetar burst.
Oh yeah, you should use the microphone.
Yeah, so if you have these pulsating ULXs powered by magnetars, they're still accretion powered. And if you posit that the radio burst would be arising from the heart of these systems, they would just absolutely not escape the accretion disciplines. So you will not see them at all. So if you see a radio burst from an ULX, it's coming from far away distances.
Okay, great. Theory consensus instead of theory battle. Okay.
But yes, ULX.
Okay, we have time for a few more remarks on this. Any other directions?
Yeah, it's Molson again. So I have like basically complete naivete about PRSs and the continuous aspect of FRBs. But in the cases where if we were fortunate enough to have observations of a PRS that were at the same time as some kind of burst storm, do we expect there to be changes in the brightness of the associated PRS, not because of the emission from this burst storm being like included in that observation, but because physically something is happening at the source? Okay. Okay.
Yeah, so the question from Mosen was whether you would expect the luminosity or the observables from PRS to change if there was an burst storm happening in the engine, not due to observational effects, but physically. It depends on the model. If you were to invoke a magnetar wind nebula model where the PRS is inflated due to the flares from the magnetar, then yes, you would expect such a change. But in a hypernebula scenario where the flares launched from the pointing dominated jet, say, are producing the FRBs, then the PRS overall properties would barely be affected. But overall, the luminosity of the PRS would scale with sort of the luminosity distribution of the intrinsic bursts that are launched from the system.
Okay, then we'll go to Kavya, and then we'll see if there's any final remarks on this. Yeah, go ahead.
I think I just agree with Naveen. And also, I was also like thinking, why didn't we mention about the AGN scenario? Because the flat spectrum and also the long-term stability is also consistent. I mean, like the AGN, radio loud AGN can also explain such properties as I read from literature. So maybe.
You have to wait for the microphone.
I think accretion powered, I mean like AGN, which is having accretion, it can also like, if the PRS is something coming from that, then the observed stability over this like decade and also this flat spectrum observed in L band could be explained by such a system.
Yeah, it hasn't been mentioned a lot at the conference, but there are dwarf galaxies with persistent radio sources in them that are thought to be massive black holes. I think, Tarne, you've worked on this with Amy Rines quite a bit. It's not obvious that whether that's like a different population of persistent radio sources and dwarf galaxies, or whether those are just the ones where we don't see the FRBs, but it's all the same thing. Yeah. For people online, Tarne is just politely nodding. No, so okay. Vicky, you had a comment?
Yeah, just a comment. So well, I guess we haven't heard that much, unless I missed it, about the synchrotron maser model so far. And that was, part of that model was to explain PRSs in 121102. And so we heard, I guess, a talk today about how, the magnetar wind nebula would be inside a supernova. And I guess I'm sort of associating the magnetar wind nebula with, that there would be a shock there that could be where the synchrotron maser would operate if that model were applicable. And but that, that whole thing evolves with time. And so I guess what I'm thinking is you might expect different types of bursts from, that would somehow be correlated with the properties of the pulsar of the PRS, if those indeed are one and the same type of object. So if you see a really bright one, wow, that should affect the synchrotron maser model if it's, more compact or younger or something like that.
Yeah. Okay, we'll take one final comment by Naveen, and then we'll move on to the last topic. Yeah.
The shock that you mentioned, so Naveen from Stanford. So there are several shocks happening here. So there are multiple locations where shocks are happening. The shock that heats up the particles eventually that produce the pulsar wind, or the PRS, is expected to happen at 10 to the 17 centimeters, whereas the kinds of shocks that synchrotron maser models invoke to produce the FRBs happening at 10 to the 12 to the 13 centimeters, well inside the PRS. So they don't have a direct interaction in some sense. So the evolution of the shock that produces the PRS does not directly alter the bursts coming from deep within the PRS. No, they are not caused. They're not connected. As in, the engine is the same. The engine that's powering the FRB and the PRS would be the same. For example, at later times, the engine could get older and you would produce lesser and lesser bursts, and it would not pump enough material to power the nebula. But the location where the FRB is produced and the location where the particles are energized to produce the PRS emission are widely separated by over 5 orders of magnitude.
Okay, thanks, Naveen. Myles is going to take us through the last topic. And I see there's a lot of messages online, but is that just chat or? Yeah. Okay. Yeah, no, take it away. I'll take it close to the laptop as well.
All right. So we'll go into the last topic of this discussion, which is on long period transients or long period radial transients or whatever name you like the most. So we heard quite a bit about LPTs this morning. And so there are, I think I need to update this number, but there are somewhere around 11 or 12 long period transients with pulse periods that are above about 10 to 100 seconds that have been identified. Some of these are, tentatively associated with white dwarf M-dwarf binaries, but most of these are unidentified so far and don't have evidence of optical counterparts or high energy counterparts. I believe there's one that's associated with the high energy counterpart. But there's a lot of questions we can ask about, what these, first of all, just phenomenologically, I can never say that word. What lessons can we learn about FRBs that we can, learn about long period transients that we can relate to FRBs in terms of their subpopulation. So we know, just by the fact that we don't see M dwarfs associated with many of these long period transients, that they're not, at least they're likely not white dwarf M dwarf binaries. So what, there must be another channel, whether it's a different progenitor, a different source mechanism, a different emission type. And so what can we, learn about distinguishing different types of LPTs and apply it to FRBs? How can we explore the link between LPTs and FRBs and how might their progenitors be related? So I've shown a couple there, and just to give put a fine point on this, so we know that they have much longer pulse periods and fall into this region that we refer to as the death line, or further to the right, compared to magnetars and other pulsars. So it's clearly, a unique type of source, but how are they related to, say, typical pulsars, other neutron stars? If they are neutron stars, are they white dwarfs? There's a lot that we don't understand about this population. But we know that they can be related to FRBs based on things like their coherent emission, the fact they have to come from a compact source. And there's some cases that we heard about where they show downward drifting structure or substructure that's very similar to FRBs, although on longer timescales. And then finally, how can we increase our sensitivity to extragalactic LPTs? That might be one way that we can learn more about the link between long period transients and FRBs. So does anyone want to start off the discussion?
Hello, Adam Dong from NRAO. I think the things we've seen are very tantalizing, and I'm going to shoot myself in the foot a little bit here, but I think the luminosities are just so different from FRBs. Like you're talking about, I don't even know, like more than 1 trillion from factors of luminosity difference. So and how are we gonna it seems difficult to bridge that, is all I'm trying to say. And to a point of like extragalactic FRB LPTs, pulsars are brighter than LPTs in terms of absolute flux, and apart from some rumors, we haven't even detected it. True extragalactic pulsar yet. So that's my 2 cents.
Yeah, it's a great point covering that, like that really large luminosity range. And I don't have, let me see, I don't think I have the plot with, oh yeah, this one does have a couple of LPTs on it actually, so you can see where they fall on the luminosity scale again. And so covering that wide order of magnitude is difficult, but they do have some of these implied magnetic fields that are pretty high that could suggest that they have a large magnetic energy reservoir. So that's one way that you could, source that energy. But does anyone else have any? So if you have a couple of comments, maybe we can go to Mawson.
Yeah, it's Mawson here once more. So I guess like a case study counterpoint to that is things like thermonuclear explosions, right? Where like in our galaxy, we see classical novae that are like probably dim enough to not really be observed over a cosmological volume. And then conversely, by like basically the same emission mechanism of blowing things up, we're seeing them over wide redshift ranges, even further away than FRBs. And so I think it's like, especially on a plot like this, where you're plotting all your data points, but what's important is the rate at which they're observed, which is completely obscured from this. Is I think it's easy to trick ourselves that that's a really vast gap that like maybe we can cover. And like your point's totally well taken in that, you haven't seen extragalactic pulsars. And so clearly there's some luminosity function that doesn't go all the way up to there. But like, I don't know, does that tell the whole story? It's hard to know.
I mean, there's such a wide range. It is definitely hard to tell. We'll go over this way next.
I'm going to disagree with Adam. And yes, before I disagree, I should introduce myself. I'm Calvin from UC Berkeley. I'm going to disagree with the point that a large luminosity gap is hard to explain on the basis that this is radio luminosity. But an easier way to get a million times the luminosity as a radio photon is to have one optical photon. So I want to emphasize that I think the multi-wavelength counterparts are going to be really important in figuring this out. And that if you made the same plot with total rather than radial luminosity, things might look very different.
We'll go over to Naveen.
Yeah, I have to introduce myself before I disagree with Calvin. Naveen from Stanford. So even though it's a million orders of magnitude or trillion more than the typical pulsars, you said it's just simple radio, but the more relevant parameter here would be the wave strength parameter, the amplitude of the waves as a ratio of the moment of the particle's mass, basically. That exceeds unity for FRBs, and that gives rise to completely new plasma instabilities and phenomena that you would never see in sub-unity or less than one wave strength parameter regimes like pulsars and so on. So this is entering a completely new physical regime. So you would need new ways for it to be emitted, for it to be transported outside certain regions and so on. So it's completely new physics, I think.
We have a hand online. Alex, you can go ahead and unmute.
Yeah, hi, Alex Cooper from University of Oxford. Just on the luminosity gap, I think in terms of the kinds of energies you need to perturbate a magnetosphere or the crust of a neutron star by, these are very gentle changes that you need to get to the kinds of radioluminosities that we see for LPTs. And so, increasing this to much more radical changes to either the crust or the inner magnetosphere of a neutron star, you can get to those FRB luminosities relatively easily if you're assuming that these are relatively violent events compared to the LPTs that we're observing in the galaxy.
So if I could poke the bear a little bit, if it is these gentle changes that we're looking at that can get us to higher luminosities, what could explain, why we're not seeing brighter, say, long period transients in our galaxy, or brighter magnetars, for example.
So
I'm not sure I heard during the conference anyone like really explaining what the emission mechanism is for instance, the LPTs that have been shown to be in these magnetically locked binaries. It seems to me, especially since the pulses are seen at conjunction, that it has to do something with this magnetic bridge between the two stars, right? And to me, at least, that is kind of like a proof of existence that maybe you can get coherent emission from this kind of like almost like a linear accelerator between the two stars. And if so, why not like a magnetic bridge between two white dwarfs that are in like a 5-minute orbit, or like two neutron stars, or a neutron star and a more massive companion? Like there might be some analogies to that would just be enormously more luminous than what we've seen in our own galaxy. And now the theorists can tear me to shreds. Okay, which one first? Okay.
and on that, and just on that note, as well, in I believe it was Iris Deruta's talk earlier today, where you can have emission at different phases of evolution as well, and that might give you a different luminosity or a different behavior. Yeah.
So on the binary scenario, I would like to comment that our work, Alex's work and Zorawar's work, has shown that you need very small binary separations. Oh, by the way, I'm Om Gupta from UT Austin. You need very small binary separations to actually achieve the potential for accelerating particles to such high energies that we see the fluxes at large extragalactic distances. You need very small separations, especially for neutron stars. So for white dwarfs, that situation is further exacerbated.
Someone have a comment on that? Oh.
Just to continue Jason's line of thinking, maybe the theorists can tear me to shreds later.
Introduce yourself, please.
Barak Zakai. So maybe if you go into locked systems of compact objects, you are also tapping a new source of information, which is the orbital energy. And that could give you a source of information that is much larger than what you have from the rotation of the neutron star.
Over to you.
Thanks. You're even labeled from ASTRON, so if you will allow me to be provocative, I think much of the excitement is because we are discovering LPTs and FRBs roughly at the same time. If someone would discover the pulsar 0950 plus 08 next week, we would all be standing up, shouting and screaming in amazement because it has huge pulse-to-pulse variability. It has downward drifting, it has upward drifting, but it's been in that pile for so long that we kind of forgot. So let's be also realistic. How much of this is just the timeliness of it, and how much do they really tell us about FRBs?
Yeah, that's a great point. I mean, we'll go back to Wayang, and while you're doing that, the recency bias, I think, in astronomy is very strong, let's say. Yeah, okay, so we'll do 2 more comments.
Okay, just short comments. We are from University of CS. So I just gave a short comments of the periodicity search. So we haven't detected any confirmed the periodicity. Even we have a large burst sample. So for instance, we have detected more than 10,000 burst samples from the FRB 2024-0114. So, but we haven't detected any confirmed the periodicities. So I guess here actually we have tried so many methods to find the periodicity, but but there is no confirmed signals here. So from the physical side, I guess there is actually no periodicity can be seen. Even the FRB source is a rotating pulsar or magnetar. So because the emission maybe came from random regions from the star's surface. So rather than the pulsars, they are confined into the polar cap regions. So that's short comments here.
Yeah, and I think we're just about out of time, so maybe we'll continue discussion over the coffee break. But just a hand for everybody who for all of our great discussion here. And I look forward to continuing over the coffee break.
Yeah. So
that's my fault.
So it is not a coffee break.
No, that's my fault.